brain in common. They all research the brain and how what we know about it could be used in schools. They all have different passions and different ideas of how to change the school day. And they found that teachers are the people who can best use their ideas.
Teachers are the only professionals that on a daily basis are responsible for changing the structure and connectivity of the brain.
Some of their radical research has already been tested in the classroom.
You have to write a presentation which is radically different than anything else that you've done.
And some doesn't even seem relevant to education. Not all the scientists are agreed.
Any idea that you can have a neuroscientifically based educational program seems to me to be fantasy.
But this program is going to let them have their say. Monks Eton High School near Newcastle upon Tyne. It's exam time and something rather unusual is going on. These children are about to begin a revision lesson. But because of the latest neuroscientific research, the teaching is far from conventional.
So this first one, I just want you to totally focus on the screen and absorb as much of it as you can as I go through it. For about 10 minutes, I'll deliver a PowerPoint where they just sit and listen and absorb the information. LDL lipoproteins, they are bad for you, right? LDL is bad. After approximately 10 minutes, they'll stop and they'll do some physical activity for exactly 10 minutes to give the brain a chance to rest. So you're using another part of the brain, not the part you've just been using when you were learning.
These children are trialling what they call spaced learning, which uses 3 intensive blocks of teaching interspersed with activity breaks, all within a 1-hour lesson. It's based on our knowledge of how the brain works and what scientists call long-term potentiation. Memory scientist Terry Watson is our first scientist to have his say into how he thinks neuroscience can influence education. A researcher from the Open University, an expert in long-term potentiation, he's the brains behind what's going on at Monks Eton.
So supposing you've got 2 neurons, and this one is talking to this one. And what you do then is you put an electrode into this neuron, and you give it a brief burst of impulses. This neuron then responds in a particular way. It gives its own pattern of impulses.
They've discovered that the more the first neuron is stimulated, the stronger the response in the second neuron.
So the whole idea behind long-term potentiation is that you can maximally stimulate this particular neuron to alter the firing characteristics of this neuron. So in other words, you have some sets, 2 or 3 sets of stimulation with gaps in between, and you get a maximum response from the cells that you're interested in.
The problem is, long-term potentiation has only been shown to work in laboratory rats. This is where Monks Eton's head teacher, Paul Kelly, enters the story.
On a train journey back from London to Newcastle, I happened to pick up a copy of Scientific American. And in it was an article called Making Memories Stick. And I thought that would be really good in school. We could do with making memories stick.
Paul Kelly isn't what you might call a conventional head teacher. With his office in the middle of the library, he's happy to buck the conventional methods of teaching, and his starting point is the school timetable. This old Victorian school timetable is not so different from the school routine teachers and students follow today.
At the moment, we're at a crossroads between a timetable which has really been built 2,000 years ago in Roman days and a understanding by neuroscientists of the way that people really learn and how they develop best as human beings. And we're going to have to change.
Seeing how science might be able to reform his school timetable, Paul wasn't one to shy away. And the first thing he implemented, with the help of Terry Watson, was his spaced learning lessons.
Because it's a gas, it's going to affect how oxygen's carried in the blood. If you lack in vitamin D, you will get rickets. Nicotine is bad because it's addictive.
In all cases, those that received revision simply through the spaced learning technique did at least as well as the kids who were getting normal revision, and at least as well as the kids in the rest of the country.
After 10 minutes of learning, the children have their first break. It's at this point that the neuron connections that have been made during the learning develop.
Spaced learning is not easy. You have to construct a lesson fitting in with the scientific research, which is the 2 10-minute gaps and 3 repetitions with a degree of variation. And you have to write a presentation which is radically different than anything else that you've done and compresses an enormous amount of information into a very small period of time. So they have to be quite carefully crafted.
It's really hard to manage. You can't do it if you haven't got good classroom management. You have to be able to have them silent and be able to pull them very quickly and be back on what you're doing without letting it stop your train of thought.
The idea is that the breaks allow the reinforcement of the neurological connections made during learning.
What happens when we have learnt something, soon afterwards then all of the relevant connections are being reinforced, and you're giving those neurons the opportunity to do those things whilst doing something else. What that other task needs to be, we don't know. Playing basketball is one option because you're using a different part of the brain.
The children return from their 10-minute break and Angela takes them through the same PowerPoint again. The theory is that the children will now remember more about the subject.
Receptors in the skin detect what's the start of the pathway? Stimulus, well done.
However, there are those within the scientific community that aren't as enthusiastic about changing education in such ways. Professor Stephen Rose from the Open University is one such scientist.
What we do know as neuroscientists is that in some animal experiments, in the sorts of learning experiments you do with animals, which is learning to run mazes or to avoid electric shocks or something of this sort, then if the animal is given a very quick set of repeated trials of the task and then given a consolidation period, and then is given the trials again, then they learn in a different way from if they're given the whole batch of trials all at the same time. But to extrapolate from that to saying this is a way you ought to be teaching children at school seems to me to be fundamentally irresponsible.
The ethos is first do no harm. We've got to make sure that all of the children who are participating in the spaced learning do not suffer as a consequence, and all of the evidence says that they do not. And from my looking at the data, it's looking extremely promising.
Right. Am I an animal? Yeah.
Back in our spaced learning lesson, the children have just finished their second break.
We're going to go back to this for the last 10 minutes.
And are beginning their final section of learning, where they fill in a sheet, testing them on what they've remembered.
It's a way of learning for a particular purpose, and it has particular strengths. Should other schools try it? Should other schools test it? The answer is yes, very definitely.
It isn't constant learning, it's you have breaks from them, so you've got time to relax.
You're not sat in silence, just trying to read out of a textbook or something. It's more fun, it's interactive, so it's better.
It's good all round.
One of the reasons neuroscience could start to have an impact in schools is because we can now study the brain in much more detail.
Neuroscience is a hot topic at the moment because it is in many ways one of the last great frontiers in biology, and the new techniques that have become available from genetics, from molecular biology, from imaging have now made the brain accessible in a way that it's never been before.
One of these new techniques is called MRI scanning, or magnetic resonance imaging, which actually allows scientists to take a look inside the brain as it works. One man who knows all about MRI is our next scientist to think he can have an impact on schools in the future.
Well, MRI is a big, expensive machine. It's a huge magnet. I'm able to depict very fine-grained the structure of the brain. It's almost like a big microwave without the effect of heating, of course.
Bogdan is a researcher in what scientists now call brain plasticity, a concept which is showing students that academic success is in their own hands, or rather their own heads.
Brain plasticity. The idea behind it is that the brain is not a static structure, and when we learn something, both brain structure and function are changing.
What got Dr. Dragansky interested in the relationship between brain plasticity and learning was some research into a rather unique group of individuals. Research into the brain scans of London taxi drivers showed that a certain area of the brain was different from the norm. And this area related specifically to spatial skills and memory. To become a qualified taxi driver, a person must learn over 400 different routes in London, a feat of memory that is known as the knowledge. In drivers with the knowledge, this spatial area was found to contain many more neurological connections than in people without, suggesting for the first time that the ability to learn is directly associated with brain structure. What scientists didn't know is whether the drivers had this specialized developed area from birth, or whether it developed as they learned the knowledge. This is where Dr. Dragansky took over.
As we thought about some interesting and more funny way to motivate our subjects to learn something instead of just asking them to memorize some numbers or words, we decided for juggling, and they confirmed it was fun.
Dr. Dragansky and his team asked their subjects to learn to juggle for 3 months. Then they tracked the subjects' brain structure as they learned.
This is the back of the brain, and exactly in this area, this is a higher visual area. Here again another shot of the brain from the back. In these areas we found the change, the expansion of the grey matter. The direct impact of our research was that it showed for the first time that the structure of the brain is changing while training or learning something new. Even in a higher lifetime, in our 5th or 6th decade, while learning, the brain structure is changing. It means the brain plasticity is still ongoing.
This has big implications for what goes on in the classroom. Paul Howard-Jones is our next scientist to have his say. He's looking at how teachers can use this knowledge of brain plasticity.
The thing is that actually teachers are the only professionals that on a daily basis are responsible for changing the structure and connectivity of the brain. A lot of people see the brain as some sort of biological limit, if you like. You know, I can't do it, it's my brain. That is really not the case. There's no reason why anything that we understand about the brain should limit achievement. Far from it. In actual fact, knowing about the brain and knowing about its plasticity can actually influence the learner's approach to their work and their self-concept. Another way of putting this is that biology is not destiny. And that's a really important message.
Is this something that could come into teaching in the future? Maybe schools could schedule lessons teaching children about this plasticity, letting them know there are no scientific limits to their learning. One effect the concept of a plastic brain structure has had is to dispel the popular myth that people's brains stop developing past a certain age. And that has opened up a whole world of possibilities for learners.